Okay, here we go for part 3, folks. This question is the big kahuna, the grand cheese. So let's get at it. Find the particle's initial position, initial velocity, initial acceleration. That word initial just means at time 0, right? Time 0. So a bunch of quick calculations and interpretations here. S at 0 is 0. I just put in t equals 0 and I get that. Take the first derivative and I get 12t minus 3t squared, and then I substitute 0 and I get 0 again, which means it stopped. S is 0, means it's at the origin. V at 0 means it stopped. It's 0. And then when I found the acceleration function, take the derivative of that, 12 minus 6t, and I sub in 0, I get 12, which means the acceleration, even though it stopped and at the origin, is to the right at 12 meters per second squared. All right. We're going to have to squish this in here too, folks, so I hope you're okay sort of flipping back and forth. B, find the particle's position when the velocity is 12 meters per second. Notice you have to read carefully to see what's going on. You know, we're given the velocity is 12. So we're given V at t, V at t is 12. And what do we need? What's required here is I want to find S at t such that this is true. So that means I got to solve this equation, find out what t is, and then calculate the position then. All right, well, no problem, because I've got my velocity function is 12t minus 3t squared equals 12. Put that all in one side. A little quadratic equation action. It's always a nice day for that. Divide everything by 3 first here. Ooh, and it looks like this one's actually a special case. This looks like it's if I factor this, I get t minus 2 all squared. Take the square root and positive negative 0, right? That's just 0. That's stupid to write that there. But t equals 2. So therefore, then I have to put it, calculate the position. S at 2 was, I just substitute in and calculate. I can't see it though because it's way up there. Way up there. S at 2 is 6 times 2 squared minus 2 cubed is, bing, 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 I get 16. So, and then therefore, the particle was 16 meters, I guess. And it's positive, so that means right. The position is positive, means it was right when it was moving 12 meters per second. I use the 12 meters per second that was given in the question. And these sorts of things, I have to be careful about what I'm given and what I can find. I'm going to copy these questions and go, can I? Yeah, I'm going to scroll back up and down. Actually, I'm going to copy some. Copy, go to the next page, paste, just so I have more room. This is C. C. Find the time position when the object is at rest. The object is at rest. What does that mean, the object is at rest? This is V at t equals 0. Stopped, at rest. Okay, so that means I want to find the time and position. I want to find time and the position when this is true. Well, what was my velocity function? My velocity function was 12t minus 3t squared. So I got to find out when that's 0. 12t minus 3t squared equals 0. Factor out a 3t, and then I get 4 minus t equals 0. T equals 0, and t equals 4. So that's my time, and I got two different values then. S at 0, remember, was just 0. We had that one. And S at 4, well, little calculation there. Where was the function? 6 times 4 squared minus 4 cubed is bing, bing, bing on the calculator. And I don't have my calculator. Darn, I'm going to actually have to calculate this. That's 16 times 6 is 16 times 6 is 36 and 3. I should have had a calculator. 96. 96 minus 64 is minus 64, rough work, right? To 32. So that means the object was stopped at the origin and also 32 meters to the right, right? And that was after 4 seconds. D. When does the particle change direction? When does the particle change direction? When does the particle change direction? Well, notice that's after it stops, probably, right? So now I'm thinking, I've got this, and I'm going to put this all together on a number line later. But if I have, think of my velocity at zero, and after 4 seconds, it was also 0. And in between, I can see, because there's my velocity function, right there. In the test points, I could try test points. If it's 2, say, there's my test point is 2. When it's 2, 6, and 4 minus 2 is positive, it's going to be positive. It's going to be positive all the way in here. And then I'll bet you it's negative out there. So if I put in a 5 there, that's negative. 5 there, it's going to be positive. And then the velocity would be negative there. So when does it change direction? Changes direction if we consider only after 0, the particle changes direction after it stops, right? It makes sense. It's also the same spot as it was came to rest. Four seconds. Next, what's E? When does the particle return to its initial position? So initial position, that's when S at t equals 0. So now that means we got to solve this equation. Isn't this fun? This feels a lot like advanced functions to solve these polynomial equations. So factor out a t squared, 6 minus t equals 0. So after at time equals 0 and time equals 6, it's at the initial position. Particle back at origin. F. Phew. Huge example. Grand poobah of examples here. Construct a sign chart. So what does this mean? I'm going to do a decent job of this. I'm going to draw a straight line for a change. Well, this is a sign chart, but this is a big sign chart because we've got 3 functions. We've got our position function, and we know at the time 0, the position was 0. After 6 seconds, it was also back at the origin. And what happened in between? Well, let's have a look at this. In between here, we've got values like 3 and 4 and stuff like that. It's always positive in here, isn't it? All these values would be positive. And as soon as the S gets on the other side of the 6, it starts becoming negative. So it's to the right for most of this particle's journey. Well, let's think about the velocity. There was the velocity sign chart. There was another important value here at 4. So I'm going to put 4 in there. 4 was where the velocity was 0, but it was 0 at the origin there as well. And then negative after. Okay. What about the acceleration? We haven't done the acceleration yet. Let's think of the acceleration function. What was the acceleration function? We actually calculated it back in A. The acceleration function was 12 minus 6t. So let's add the acceleration function to this. So here, acceleration function was 12 minus, when is it 0? That's when it's, the velocity is constant. So solve that little tiny thing that's at t equals 2. That's when that's 0. And what about, here's the acceleration function there, for values less than 2. For values less than 2, like 1, and at 1, it's positive. Well, that makes sense because I remember calculating the initial acceleration to be positive 2 as well. And then after 2, I think values like t equals 3 or 4 or 7 or 18 or whatever, always negative. Right? And this sign chart will allow us to get a good picture of what this particle is doing. And there's the sign chart, and it says, illustrate the particle's motion on a horizontal line S. Okay, now this is difficult to do because if I say, well, it's, and I'm going to do this, and we're going to do a better job of it in a second, okay? If I go, well, it starts at the origin. Here's the origin 0. Then it goes to the right, and then it turns around and goes to the left. And then if it's going back and forth, it just gets ugly. So what we do is we kind of move a little bit down just so we can, or down or up so we can read what we're doing. So here's the position model. So at time 0, the particle is at 0. So this is time 0, it's at 0. And then it starts moving to the right. Okay? Starts moving, whoops, a little bit wobbly. That's okay. Starts moving to the right, and then after 2 seconds, what's weird is the acceleration is no longer to the right. It starts moving, it starts getting pulled left. So that means it starts slowing down, right? And then at 4, the particle stops. V is 0 at time equals 0. It stops. And then what happens? Well, it starts moving left. Starts moving back left. Starts moving back left. It starts moving back left. And then eventually at time equals 6, the position is back to 0. And then it keeps going. Time equals 6, S equals 6. So, you know, a little bit strange there. Here, the acceleration is 0. But what happens? There I can see right there, because the velocity and acceleration were the same, it's moving right and speeding up, right? Because the acceleration and the velocity are the same values. Here, it's moving right but slowing down because the pull started to be to the left. And so if it's slowing down, eventually it's going to stop. And that happened at time equals 4. And then, because the pull was still left, it stopped and it started pulling left, and then it was moving left and speeding up. And it kept doing that, and it flew past the origin at time equals 6. What a great question. What's the last? There's a last little bit of business. The object was compare your graph with the answer. Graph the position function s at t. Notice that in functions class, advanced functions class, we would have got this and graphed it right away and hoped we could figure out when the minimums and maximums occurred. But with this, we can do a lot better than that. For the position function, we knew it was, do I got a different, I'm going to use a different color. 0 there, and this is position, not velocity. And then it was back to 0 there after 6 seconds. And then it reached its maximum at 4 seconds. Right? 4 seconds. So it went something like, because it was speeding up, accelerating, moving right and accelerating, so it sort of goes like this, and then it gets to a certain spot, its maximum, and after 2 seconds, by the way, it starts slowing down, and then gets to its maximum, velocity 0, and then quickly moves down, velocity is negative, decreasing, and then goes through the origin. And notice that this matches what we knew the function would look like, because from our advanced functions techniques, we knew that would have a 0 here, slash root there, and a bounce there. And in fact, we even know all these values this way because this position here went, how far out did it get? Well, at um, a time of 4, we did a calculation back here, didn't we? Time of 4. Where was it? Time of 4, the position was 32. So the maximum was 32. And in fact, their velocity is 0. The position was 32 before it started moving. Remember back in functions when I said, we're going to be able to find the maximum in MCV4U? Well, that's where you are. All right, big long lesson. Not as much homework though. Okay. I hope you got through the motion stuff again. There's an example or two in the textbook in case you're struggling, but there we go. That's all I have to say about that.